All right, acid-base basics. We're going to start off with your typical acidic equilibrium. We've got HA, your acid, dissociating to form H3O plus a base, A minus. This is all determined by your Ka values, or your Ka value. Ka value is going to be assigned to HA. What you really want to understand is the higher the Ka value is, the more dissociation you have, stronger the acid. Okay, so the stronger the acid, the higher the Ka value. For the sake of convenience, there's this convention for Kas. Instead of reporting them as Kas, you can report them as pKas. And all the pKa is it's the negative log of your Ka value. Okay, so pKa equals negative log Ka. General thing that you want to take away from this is the lower the pKa is, higher the Ka, and then this means stronger acids. Okay, so it's an inverse relationship. Higher Ka, lower pKa, stronger your acid is going to be. All right, so Ka and pKa, they're going to be fixed and they're assigned to HA, all right, your acid. They're fixed for a given acid. It measures how likely that acid is to dissociate, aka the strength of the acid. Okay, with this base, the conjugate base, you could assign a Kb and a pKb. All right, measures the same thing, except with bases, Kbs and pKbs are how likely something is to get protonated. And there's also an inverse relationship such that pKb plus pKa, for conjugate pairs in aqueous solution, it must always equal 14. So stronger the acid is, weaker the base. Weaker the acid is, stronger the conjugate base. Okay, now going back to this whole pKa thing, there's an important equation called the Henderson-Hasselbalch equation, and this is pH equals pKa plus log AHA, all right, A minus over HA. And A minus, this is going to be your base form. Remember that the base always goes on top and the acid goes on the bottom. So pKa is fixed for a given acid. Okay, it's fixed for a given acid unless you change the temperature, which we're not going to be doing. The pH, on the other hand, the pH isn't really always due to just the acid. More often than not, it's due to whatever environment you're putting it in. Okay, so like in the stomach or the circulatory system. And based upon this pH, okay, so pH, it's a measure of how much H plus you have present. pKa is a measure of how much that acid wants to dissociate. Those two things are going to influence whether or not you have more of the base form at equilibrium or more of the acid form. Three possible scenarios. If the pH is lower than the pKa, all right, if the pH is lower than the pKa, just think lots of H plus favor protonation. HA is going to be greater than A minus. Lower your pH is, the more acidic your environment is, the more you should favor the acid form. Conversely, if your pH is getting higher, more basic, you should favor more of the base form. And then if the pH exactly meets the pKa, what you're going to find out is you'll have a 50-50 mixture of your acid and your base form. All right, so that's the general gist of the Henderson-Hasselbalch equation. Let's take a look at a specific example. In the stomach, let's say our pH is about 1.5. It's between 1 and 2. I'm going to take 1.5 as the average. So let's go ahead and rearrange our Henderson-Hasselbalch equation to get pH minus pKa equals log A minus over HA. All right, all I did was I moved the pKa to the same side of the equation as the pH. So we have two drugs, drug A, drug B, and we want to get an idea about which one's going to be more protonated at a pH of 1.5. So intrinsically, what I'm thinking, like intuitively, I'm thinking 2.5 weaker acid or stronger acid. All right, so if it's 2.5 stronger acid, you should have more dissociation. 4.5 weaker acid, you should have less dissociation. Let's take a look at this from a number standpoint. So pH is 1.5, pKa is 2.5, 1.5 minus 2.5 is minus 1. This is equal to the log AHA. Raise each side to the 10 power. So you go 10 to the log canceling out. And what this tells you is the ratio of A minus to HA is going to be 0.1. All right, so A minus to HA, that ratio is 0.1. Compare this to drug B, where we have 1.5 minus 4.5. That's going to equal -3. -3 is equal to log AHA. And then you're going to go 10 to the -3, 10 to the log. That cancels out. Now our ratio of A minus to HA is going to be 0.001. So we can clearly see when we compare these two drugs, drug B, higher pKa, weaker acid, look at how much dissociation you have relative to the drug A, which has a pKa of 2.5. Okay, it's a difference of like 0.001 to 0.1. And that's what we expect. Stronger acid, more dissociation, more A minus. Weaker acid, less dissociation, less A minus.